let's write down the four electric field, okay, with also with the time component. Let's write down everything for that. So our electric field, the total E of, if you simplify your electric field to only, you have a very component Z, variant Z, and also it is a function of T, it's a function of Z and T. A total E field, we can write down like it's E, it is a scalar, it's a scalar function, E of X, and it is a function, this is only, we consider only the positive E field. So you write down EX positive, this is a magnitude of the positive E field. Multiplied by the exponential minus J K Z. This is what we obtain from the PD equation. Okay, and because this is a function harmonic, this is a time harmonic result. So you also multiply exponential J omega T plus there is another field which is go to the negative direction, negative Z direction. So EX minus another magnitude of your refracted wave multiply exponential positive JKZ multiplied by the exponential J omega T. Okay, this is the four E field, and don't forget to multiply your total result to X direction. It's the unit vector X. Okay? Okay, I just review. So, what is this? What is this? For this, you can combine the power of this part to, you can write down like, okay, let me write down. So equals to your E field equals to EX plus exponential J omega T minus KZ. Okay, it's not very hard. Okay. Omega T minus KZ plus EX negative exponential J omega T plus KZ. And don't forget your vector. Okay. This one, you can take the real part of your total E G T. Let's take. If I take only the real part of that, I don't know, is that okay? Maybe I can check the vector way. I just want to see the function. Okay. Let me write down like, so EXZT equals to this one, and without the vector, I can write down that. So this one equals to, you got a result? EX positive multiply cosine omega T minus KZ plus EX minus cosine omega t plus kz. And there are two terms of phase. We call cosine theta, right? Okay. When we consider about the cosine theta, we are talking about this term. Another theta, and maybe I call this positive and the negative theta. There are two different phases. They are different. It is a wave. Okay. So, which component can affect the theta? Who will decide theta? Your time, because your wave is moving. So depending on if you have different time, multiply your omega. This is your frequency of angular frequency. And about another factor will affect your theta is z. What is z? Z is your position where your wave is. Multiply k. And remind you what is k. We define k. K squared equals to omega squared multiplied mu epsilon, right? So k equals to omega square root of mu epsilon. Another omega here. Okay. Mu and epsilon, those are variables relevant to the material, air or maybe water or maybe FR4, what kind of material it is. You choose different mu and epsilon. And omega, it is 2 pi f. 2 pi f. So this is what we write down. So theta, it is omega t minus kz, or omega t plus kz. And also you can take your 2 pi outside. Take your 2 pi outside to see what happens here. Because you know cosine is a harmonic function. Repeat every 2 pi, right? Cosine. You know cosine repeat 2 pi. Yeah. So every time you have 2 pi, you can repeat. You can see from that 2. We can see from this term. Omega t equals to 2 pi f t minus k is, okay, maybe let's use another. K, it is actually similar to beta. We don't use this one. If you use the k equals to 2 pi over lambda, because we call k is a wave number. Wave number means how many lambdas in 2 pi. There are how many waves in 2 pi. How many physical lengths of waves for 2 pi. So the definition of k is also 2 pi over lambda multiplied z. And you can take this outside. It is 2 pi ft minus z over lambda. Let's do something different. Do you know the definition of frequency? What is the definition of frequency? Anyone? Bonus. What is the definition of frequency? 频率的定义是什么 Anyone? Raise your hand. I can give you extra. You already got an extra pi. You know? Who else?
时间常数。
Definition. I mean definition. I need more. In English. Okay. Yeah. Okay. Chinese is fine. How many times? Oh, second for a second. This is a definition of frequency. It is the revised definition of the cycle. 周期的定义是什么？Cycle definition of cycle is how many times for one time. Yeah, if you do that once, you do that one time. How much time? How long you will take? Okay, and the frequency is 1 second. How many times? Understand? Okay. Then it's, okay. So there are a revised definition. So you can change your F to the cycle T. Okay. So your result will be very beautiful to see. You have two different variables. One is T, one is Z, right? See from here, Z and the T. Okay. For the Z, because for the physical length, you know how long it is for one wavelength. Z over lambda multiplied 2 pi is your contribution from your location, from your physical length, your space. Okay? Your contribution, 你叫 contribution 哦，贡献哦。Okay? Your contribution, the contribution of your location Z. For each lambda, it is 2 pi for your phase. Okay? So it's Z over lambda. And for your time, your contribution, it looks to the cycle. How many seconds? Okay, how many seconds? The fraction of your time. Okay, how many parts of your time? Contribution to 2 pi. So you look at that. So omega t minus or positive plus or minus kz, you can consider about the contribution of time and the contribution of your space, time and space. Okay? And I don't need to explain too much. You can see from this equation. I think this is clear than other derivations. But from the textbook, you can see that if you want to know how fast your field is, you try to, if this is the field, okay, we have this is the sine, and okay, don't care, sine or cosine function. I have the field look like that, and this field is moving to the z direction, and this is positive x and negative x direction. This one is moving. How do you define the velocity? How do you define? How do you know how fast it is? How? Anyone? The way we define the velocity of E field is we need to fix one point. Okay? We fix the point, this point. Okay, we look at this point and go and when this wave is moving to another position, you will have another wave at another point. You will see the point with the same height at another place divided, so the distance divided by your time, it is velocity. Velocity, 速度, okay? Velocity, you define velocity. So, what you do is, we try to maintain your phase is a constant. This is something like, we want the magnitude is the same. We want it is the same. So you divide it by t. We want this one equals to, if it is a constant, we take a derivation will be equal to 0. You maintain the same position. From this equation, you can obtain, you take a differential to t, you left only omega, and the minus k dz over dt equals to 0. And this term, this is the space divided by time. It is a velocity, okay? So try to see what is this from the equation you can obtain. Your velocity, this term, equals to omega over k from this. Okay? So this is another equation of phase velocity. You will see that in your midterm exam. What is how fast your wave is? Then you need to find out omega divided by k. This is one of the equation. There are more. Okay. So what is omega over k? Because k is omega multiplied square root of mu epsilon, right? From the definition of the k square. So k is omega multiplied square root of mu epsilon. Then you can cancel omega out. You obtain your phase velocity. The velocity of your field equals to 1 over square root of mu epsilon. Only determine your velocity by, you define your velocity by your material. Okay? So what is the field, the velocity of E field in the air? If you put the number mu0, epsilon 0 here, the result will become 3 multiplied to the 10 to the power 8. This is the speed of light. Okay? So the electric field in the air is speed of light. Because you put the constant mu0 and the epsilon 0 here, you can. Mu0 and epsilon 0, those are already determined, right? For the epsilon 0, it is 8.854 multiplied 10 to the power minus 12. And for mu0, it's 4 pi multiplied 10 to the minus 7. So you can multiply these two numbers, take a square root, and do the 1 over this number, it will be the speed of light. Okay? Then you can know all the velocity in different materials. If you know epsilon and the mu, then you can give me the answer. Okay? This is one of the important things we need. Okay, so this is the definition of wave velocity, and this is another way. Okay, you can look at that. If you are not familiar with what I'm talking about, you don't understand what I'm talking about here, you can put another phase. If this is your original phase, and if you have another phase, your time is your original time plus t. you have another extra phase. This is phase number 2 and the phase number 1. But the difference between the first phase and the second phase is the time is t and the t plus the capital T. Okay? And then you will know the result is 2 pi because your t is cycle, right? Your t is a cycle. So the difference between these two phases is 2 pi. Then you can do your math and then you know, oh, omega t equal 2 pi, which is omega is 2 pi over t. And omega, it is 2 pi f is 2 pi over t, which means your frequency is 1 over your cycle. Okay, it's like a reverse derivation. For there, I tell you frequency is 1 over t, and then you got the result. And for here, you put another phase, which you add one more cycle there, you get a phase is 2 pi. Okay. A similar thing you can also do an exercise like here. If your space, your location, the phase number 1 is your original phase. And for another phase, you change the location to z plus lambda. Their difference supposed to be, of their phase supposed to be 2 pi, right? So you do the same math, you will find out your lambda is Vp over f. We know this very beginning, right, from your physics. Your speed of light equals to your frequency multiplied lambda, right? You know that, right? C equals to F multiplied lambda. Everyone knows this, right? Everyone knows, everyone in this classroom knows this. So this is the same one. If you do that, the thing is, do I need to do, okay, do the details. K lambda equal 2 pi, you just do an abstraction, K lambda equal 2 pi. So lambda is 2 pi over K, right? And the K, we obtain your K from this one. K. Okay. Vp equals omega over K, right? So your omega, your K equals to omega divided by Vp. Everyone is connected. Everyone is connected. So K equals to omega divided by Vp, and put them here, you obtain lambda equals to 2 pi Vp over omega, and omega equals to 2 pi f, right? So you cancel 2 pi out, you obtain lambda equals to Vp over f. OK？ 你们应该知道这个公式吧？那个光速等于 F 乘上lambda，不是这个应该是常识嘛？频率就是你们听过频率都是从这个公式听过的吧？光速 F 等于lambda嘛，对不对？你把这个带进去，刚刚的那个公式带进去，你就可以得到你知道这个常识了。OK，let's take the rest。这些东西全部都是连在一起的，你们要很熟。考试会，考试我就直接给你一些数字，然后就是所有东西要一起算出来。啊？So there is another definition. Maybe you will see in your midterm exam. Let me ask you a question first. If there is an electric field in in the air. Okay, what is the H field? In the air means sources. Okay, if I know, if we already obtain from here, we already know our Ex is, I write down the formation, E plus multiply exponential J omega t minus K Z multiply X. If the E field has only one direction, another E field it is cancelled out, maybe matched, whatever. If this is Ex, what is H field? Anyone? This is a hard question, but you will see that in your midterm. Yeah. Maybe show it. Maybe we should show. I haven't given you an extra part yet. So write down and tell us how to obtain the H field. Electric field and the magnetic field, they will appear, they occur simultaneously together. If you have E field, you will have H field. How do you calculate H field? H equals to how? Which equation we will use to obtain? Tell me the equation. Do you know the equation to obtain H? This is another method for you. Yeah, I give you E. You already have the answer of E, right? What is H? Write down H. How? You don't know? Tell me the equation first. Which relationship you will use? Write down the equation first. You know?
他是问哪个 equation 就直接写 cos 就好了，就第一条那个框起来的 equation，就直接写 cos
equals to
就是 h 啊，
not only H, right?
就最后就他就是这样写，为什么？就是 hint 啦，为什么要有那个 equation？
What is the relationship between electric field and H field? What's that? What is the relationship? Which equation you will use? Which one? The first one? Yes. Write down. Just write down. So. Okay. But for our case, it is Ex only, right? So you put the X here. And your B equals to UH. Okay, good. So your question is, what is the curl Ex, right? Can you write down the curl Ex here? Put the O. You put the box here. Put the box. Put the box. Yes. Yes. Good. I think I have an answer. Yes. Okay, thank you. The relationship between E field and the H field is the Maxwell Maxwell equations. Okay, you use this one, you can obtain the result. Just write it down, and then you know your EX. You have only this term, right? So you don't have EY, and then you don't have EZ, and then you put here. You put 2 0 here. What is the variable for the EX? Only Z, right? Only Z. So you take a derivation for this term. You obtain this one equals to EXZ divided by Z and multiplied by Y. Okay? And another term here, you divided Y, but we don't have a variable Y, so it is 0. So this one equals to minus J omega mu. Vector to vector. So actually, your H field has only Y component. You know this Y is because from here. Let me write more beautifully. So your result of EXZ equals to minus J omega mu. Hey, show a mu. Mu, you mean this.
Okay.
Not you, mu.
Okay.
And H, Y. I use only scalar, no vector for both sides. Okay? Why is this? Because you know EX is this part, right? You take a derivation to, if we don't see the time, you use only this part, it's easier. Okay? You take a derivation of Z, it is minus JK, you take a minus JK outside. Minus JK, we maintain the same part here. Okay? Do you understand this part equals to this part? Because your EXZ is this one, and you take a partial differential to Z, you have a minus JK outside. Okay? And this one equals to minus J omega mu. And then we want to define another definition between E field and the H field. You got very similar result, right?
Yes.
So
负 J 消掉。
H Y equals to E X And this one, K over mu.
Yes, yes. 6.
And if we define eta equals to Ex over Hy, it is omega mu over K. It is you like this is similar to V. This is very similar to V, and this is very similar to I, and it is R. So impedance is 1 over R.
Wow.
Yeah. So this is wave impedance, the ratio between E field and H field. Okay, obtained from here. Eta equals to omega mu divided by K. And we know these equations. Vp is omega over K, and it is 1 over mu epsilon. We know this one just a couple of minutes ago. And we put omega, it is 2 pi, omega over K, it is 1 over the square root mu epsilon, right? And then multiplied by U. Eta, this is eta, okay? You know how to pronounce it? The impedance, it is omega mu over K. And from this relation, you know omega over K, it is Vp multiplied mu. And the Vp is 1 over the square root of a mu epsilon, and multiplied by mu. So this one equals to the square root of mu epsilon. So your impedance only relevant to your material, square root of mu epsilon. And also your speed, the wave speed and the wave impedance, you can just tell me what is the material is in the air is 377. You can put a number in the impedance of a wave. So if I give you an example of the E field, you need to write down what is H. 会不会这一题？期中考一定考。I will give you exactly what the E field is, and you give me exactly what I need all the numbers. Huh? So you open book. Okay? Right? Understand? This is a. Your electric field. Use the equation, you will know. This is the direction your wave move, and this is the direction of your E field. Then the blue one is the direction of the magnetic field. So it's supposed to be this one cross this way. I think this is a little bit wrong. And this is a little bit wrong. Should be this one cross E cross M. I think direction goes to this way. This is not correct. So this is the direction of E, direction of H, direction of the wave moving. Okay? If you have a question, raise your hand like him. Like, I think it's very helpful for me to start. And I can use another way to explain. And if you guys don't have a question, then you can continue to another part, okay? Okay? Okay. So I have finished our first part before the midterm exam. Then I will continue our second part, which you need to remember we already taught in the first part. For the second part, first of all, I will talk about materials. We already told you about D equals to mu E and B equals to epsilon H. This one is relevant to your material.
好像反过来。Epsilon.
Sorry. Epsilon and mu. Okay. D equals to epsilon E and B equals to mu H. We already use this equation a lot. I think you guys are familiar with that. But we need to spend some time to talk more about epsilon. And also, this one you will use this very much, right? You use it a lot. And also we talk about the loss tangent. I don't know how to say that. Tangent. Loss tangent. But you key in the material of your PCB, you need a loss tangent, right? We want to know the loss tangent. And also maybe some conductivity, something like that. Okay. So this is in our first part about the material. Then we will go to the total plane wave. Okay. Okay. So I think I can do this. So the materials, about the electromagnetic materials, we can have these different classes. If we look at the conductivity, we will have an insulator dielectric material, which means the conductivity is very low for the first class, first group. And there are some materials like a metal, you have a higher conductivity, so we call them conductors. Okay, and some materials between the insulator and conductor, especially when you apply different biases on it, they will change their property. We call them semiconductor. So I think for these three parts, it depends on your different conductivity, and there are other different material. Maybe they have something. You have magnetic materials, magneto, and also some special materials is made from the human artificial materials. Okay. And we need to add one more equation except more than Maxwell equations, actually inside Maxwell equations. If you consider the conductor, you will have this term. We told you that, oh, this is sourceless. We don't have this term, right? But if I told you that it is conductor, maybe you need to think about this term. This term is for your conductor. Okay, like metal or something maybe not perfect. PC, you have some current in there. You have this one more term. And for a J, you can simplify the equation to your J equals to your conductivity multiplied E. If your conductivity is very low, like a 0, you don't have J. You will have the same result as what we discussed. But if you have some conductivity, we call this is a sigma. You have this sigma, then you will have J. Okay? This is one of the new things you need to know. So, if we define the material, you can also, according to the conductivity, you can have the low conductivity material and the high conductivity material. For this one, maybe you are talking about an insulator. Your rho is your sigma is very small, so your J is disappear. And for this one, because your sigma is high and your J is larger, you need to consider about your J. Okay, so for if your conductivity is large, you think that is a metal, and the metal in the microwave materials maybe you can use to as a boundary material like a waveguide. You use a metal as a boundary to propagate your microwave. And also because the metal, it is very heavy and it's very strong. Maybe it's a carrier for all your circuit, the structure. And also it is because the metal can transfer your heat fast. You can make it like a heat sink. And also, like you are making antenna, you use a metal, you can use your metal to reflect your microwave. And for this one, you can also, I think maybe I find this material from other books. Maybe you will also have this table from your POSA. There is a table of the conductivity. For the aluminum, this is a table of the resistivity. Resistivity is the definition is conductivity equals to 1 over resistivity. Okay, so if you have a higher conductivity, you will have a lower resistivity. Okay. The definition of conductivity is J over E. And this is a list of resistivity. Okay. Alright, and this is a table of conductivity and the temperature change. Okay. I think let me just pass it. Besides, one of the things we need to consider, we need to know is the skin effect. The skin effect is if I have a waveguide, if I have a microwave and pass through a waveguide, actually your electric field will only penetrate to the skin of the waveguide. You know that? if I have a waveguide, rectangular waveguide. Okay, I use the waveguide as my transmission line, and I have an electric field, maybe something E, H, and P. I have a field inside that, and my energy is going through my waveguide. Okay. The field they have a little bit inside my metal, a little bit inside the metal. So we call this skin effect. Inside the metal, electric field will be inside metal. How much electric field will be inside your metal? It depends on your skin depth. The skin depth, you calculate the skin depth by this equation, the square root of 2 over omega mu, and this is sigma. You put a number of sigma here, you put a frequency and the mu of your material here, and you will know how deep they penetrate from here. Okay? So what can we use from this equation? If you design your waveguide, like a shower, you design your waveguide circuit. Sometimes you use aluminum then you put a number of aluminum. You will find that the sigma of the alumina is not good. So this number is not large, it's not very big, which means your skin depth is high. So your wave will attenuate. It's getting slow and slow, and smaller and smaller. It's not a good stuff to do that. So what we usually do is we use the coating, 电镀 coating. We use a coating technique to have some material has a beta sigma on the surface of a waveguide. Okay, which is always very expensive, like a silver. Use a silver and coating on the surface of that. But how much you will spend, how much money, it depends on how thick your coating is, right? You want the minimum price, so you need to calculate the thickness to understand how thick you need to coat the silver. You understand? So this is one of the important equations, especially when you calculate like an antenna, you will use these equations. They're very important. And for the in the industry, they will not just directly use this number as a coating depth. They will use like a 3 or 4 times of this number to coat in case you got a trouble. Okay. Okay. So this is so if your sigma is very high, go to infinite, your skin depth is 0, right? If this is very perfect conductor, all of your E field will inside the air. No one go to your metal. Okay? So, okay. Then now we are going to something more important. The dielectric part is always we try to calculate. If you calculate the air, you use mu 0 and epsilon 0. But if you, for example, if I tell you it is water and maybe FR4 for some material, you will use different mu and epsilon instead of mu 0 and epsilon 0. This is when we use the boundary conditions to solve the problem, which means you have two different materials, right? So you need to calculate. And the equation is your mu equals to mu 0 multiply mu r. This is the ratio of your material multiply your mu 0. And the epsilon equals to the same, epsilon 0 and epsilon r. If it is air, epsilon r is 1. So epsilon is epsilon 0. But if there is something different, you use epsilon r, you multiply the number here. Your epsilon will be a more complex number. Okay. If you choose your mu and epsilon as a real number, which means you think this is a lossless material. When you do a simulation to design your circuit, I think most of you set up your epsilon r equals to 4.2, right? As your FR4. Actually, it is not very correct. Your epsilon should be a complex number instead of a real number. But you also input the loss tangent. And for this part, we are trying to explain epsilon r and the loss tangent, what they are. So put a number in. So, when we talk about the dielectric material, which means your conductivity is very, very low. You apply your E field in this dielectric material. Inside the dielectric material, there are dipoles, positive and negative charges. Do you guys know the difference between conductivity and the dielectric materials? When you apply your E field in the dielectric material, your dipole will turn but won't move. But if you apply your electric field in the metal, the charges, positive and negative charges, will move. Do you guys know this one? The difference between these two? No? You guys? No? You听不懂是不是 ？Difference between conductivity 跟 dielectric， 导体跟非导体给它加电场的时候不一样，你不懂啊 ？You guys don't understand？
中文讲就懂。
啊，中文就懂，所以是英文的问题。If this is a material of metal, okay, metal, I apply the E field on it. The charge, positive charge, will go to this, and the negative charge will go this. We call that free charge, 自由电子，自由粒子. They will move to two sides. Okay, this is a metal. But if this is a dielectric, GNT, if this is dielectric, all of your charges will, I don't need to draw. This is if this is dielectric, they will bond at all the dipole. Your positive and the negative charge will bond at your location. They will not move to the edge of the metal. They will just, when you apply E field, they will just turn. They will just turn, okay? Do you agree with that? Okay, that's the result. When these dipoles, when they turn, you can regard them like there is another thing. We call it the polarization vector, something extra, more than when you apply to the air. This part is when you apply your electric field on the air, the electric flux density, the contribution of the something from the air, okay? And for this extra term PE came from when you have this polarization, this dipole, this is the contribution from this term. Okay. So your D equals to epsilon 0 E plus PE. This is extra, this is air. And your PE, you can define that as this is your original term multiply your chi E. This is not actually, we call this chi. Okay? Some term multiply epsilon 0. Okay? And you can reorganize it because you have something different. We call this electric susceptibility. And this term, it can be complex. Not only the real number, but also they have an imaginary part for this term. Okay. And so your epsilon, you can write down like this way. You have the real part and the imaginary part, and there's a negative term. Okay? Those are the reasons why it is negative, because it's damping, and there's a loss. And this term is positive, and so we take a minus term here. Loss tangent. So after we get a result, your epsilon, actually it is epsilon prime minus j epsilon double prime. This term is the real part, and this term is the imaginary part. We put it into our Maxwell equation. Your j omega d, we need to consider the j. Your d, your epsilon now equals to epsilon prime minus j epsilon double prime for your epsilon. And for your E, for your J equals to sigma E, I told that in the beginning of this part. So your Maxwell equation, curl H will equals to this term multiply E. Okay? And for this term, it's a combination of your complex epsilon and conductivity, this term, we define the loss tangent as the
real part of this term divided by the imaginary part of this term. This is how we define loss tangent. So you finally think it is useful, huh? This is how you key in 0.01 for loss tangent. This is how we do that. So if your conductivity is sigma, your loss tangent is only the complex, the imaginary part divided by your real part.
Okay.
This is how I try to explain the epsilon r and the loss tangent.
Okay. 这边
So your microwave materials, we always, we are very often, we usually characterize the material. We need to input those properties. We need to input the epsilon r and the loss tangent. Those are, when you design circuit, you need to know what the circuit, the material is. You need to know the epsilon r and your loss tangent. And your epsilon r, it is relative permittivity because it is a relation, some number, constant number of your material multiply your epsilon 0. Okay, so we call this relative permittivity, relative epsilon r. And the loss tangent is something, the real part divided by the imaginary part. And most of the material you use mu r equals to 1. If there is we don't consider some magnetic material, you use mu r equals to 1. This is a number of the dielectric constant and loss tangent. Epsilon r actually and the loss tangent, they are a function of a frequency. They will depend on the frequency. When you use different frequency, maybe those number will be changed. So you need to specify the frequency when you use the epsilon r and loss tangent. Okay, but if you want to decide, sometimes you input a number. If you take care of, you are very careful to look at that, you will see that there is some place to input where is your frequency when you use your epsilon r. What is your the central frequency when you use this epsilon r? Because your epsilon r is supposed to be changed according to the frequency. Okay. All right, let's go to a more complex part. We have already derived the equations for the lossless materials. But now, because we know J equals to your conductivity, sigma multiplied to your E, we already know this one, right? So what is, if your wave is inside a lossy material, what happened? Let's go back to our Maxwell equations. If you have the sigma, you need to consider your J, this term. I've already told you at the beginning of this last class. You need to consider this term. What happened? And many things will become more complex. Let's do the derivation of the Maxwell equation again. First, we take another curl to your curl E, then you will obtain similar thing when we are doing the lossless case. But this equation will be different because of when you use the curl edge, it is not only j omega d. You need to consider also j, so you need to have the extra term here. You have extra term, sigma e. So your result is not beautiful. It will become more complex. You have the extra term. Finally you obtain your, for left side is the same. You will let this term. This one is 0, right? Still 0. For this term it's okay, but now you have an extra term except your omega square mu epsilon, which is k squared. Not only k squared multiply e, but also you need to consider minus j omega mu sigma. But if your sigma is 0, you don't have this term. Okay, so when you have the extra term here, your wave equation will become this. You have this. This is the extra term, and you have your material is lossy. Okay, your material is lossy, and this is the bottom one is lossless case, and this one is a lossy case. You have the red box part, which is very, I think maybe annoying. Okay, how we deal with that? First of all, the scientists think about this question in a more complex way, because you need to you try to describe your wave. We think, okay, the wave, it is a cosine field, right? It is a cosine field. If this is a lossless case, your E field here, you can think like this is a magnitude. This is cosine, right? This is a cosine. And then you have a, you can write down, it is a magnitude of E of Ez, Ex, and the function of Z. And this is the direction Z. And then your wave will look like the K and the Z determine what the how can I say that? How fast or how many times the frequency is very similar to, this is also said in English. Let me just use 那个苏跟密，我忘了英文怎么讲。苏跟密 the KZ. This part, this is determining the phase, right? The KZ is a phase. So your phase determine your shape. How many you make it the phase of it. And what is your E plus? E plus is the magnitude. It is not 1. This is the magnitude. EX. So the peak to peak is 2EX. How big the wave is. For the sound, if your frequency is higher, you feel like this peak, this tone is very high. And if the magnitude is large, you mean the sound is very large. So it's a little bit different. This term determine this, and the E plus determine how large it is. So they want to maintain the same property of this equation, but they want to describe what is the magnitude, the attenuation property of the magnitude. Because when my wave is propagating, my magnitude will getting smaller and smaller, right? You guys know this one, because the energy is getting less and less. Your shape is maintained the same, but how large the size, it is getting slower because your energy is getting less. Okay? They try to describe this result. They use this new complex propagation constant gamma to describe it. You guys understand? This is very important. For this part, you use JK only, right? But JK, your KZ can only describe this. You want to describe how big it is. You need something, real part, outside this term. This is the imaginary part. You will not change because it is cosine. You don't care how much it propagates. They will maintain. They will maintain your E plus, the magnitude of your E plus. They will not change. But if you want to change that to describe the nature property, you need something real that. And we need to have the constancy that your result is the same as what we described in the lossless material. Okay, so you have this new definition we call gamma, which is very, very important. Gamma equals to alpha plus j beta. The beta is k before your midterm. Beta is k, okay? Before your midterm, I will tell you just use beta equals to k, which is 2 pi over lambda. You will also call it a wave number. And then alpha, it is a real number. The combination of alpha with your j beta, they are a complex propagation constant. If it is a lossy material, your alpha is some real number and a positive real number. And if it is a lossless, if the question tells you, oh, it is a lossless case, your alpha is 0. And your result will be the same as what we derived before. If your alpha is 0, this is 0. And j beta is jk, beta equals to k, they are the same thing, which means your alpha square must be minus k squared. Okay, because there's a j here, you put a square, it's minus here. Therefore, you can have your new wave equation from lossless case to your lossy case. Now your K is gamma. Your K square is minus gamma square here. And then you should write down your equation, your new electric field like this too. Okay, compare with these two equations. Lossless, you don't have the sigma, you don't have J. But for this one, you have gamma. You have gamma equals to alpha plus J beta. Okay? Understand? Do I need to explain in Chinese or you guys understand? If you don't understand, you want me to explain in Chinese again, raise your hand. 我就是你们不能都在等中文的，你哪边听不懂？完全听不懂还是？So this is a complex propagation constant. Gamma is alpha plus J beta. We call this is attenuation constant. Attenuation constant. And this is phase constant because your beta will decide your phase, and your alpha will decide your attenuation, 衰减 attenuation alpha. Attenuation plus J phase constant equals to the total propagation constant. Okay? Alpha. We already saw the alpha when we dealing with the skin effect. This is the same alpha. 1 over alpha is a skin effect. Okay. But the problem is, if this is a frequency dependent function, how we deal with that? You will become very messy, right? Yeah, I will not ask you this question. And maybe I just give you alpha equals to some number, that's it. I won't use this number where you will go too far. Okay. Okay, more. Now we can find the relationship about the sigma to the alpha. Gamma. Alpha, beta, gamma. Because this equation, this is what we use derived from the Maxwell equation, and this is what we obtain from this equation. So we know your gamma will equals to your j omega square root mu epsilon. You just take you put a minus to another side, take a square root. You obtain your result is this. Okay, and j omega square root mu epsilon multiply your u term, and the real part is alpha, and the imaginary part is beta. Okay. Yeah, I already told you the result from this one. Your K is your beta. If it is a lossless case, right? Don't need to think about too much. K is beta. And we already did that before. So then we need to derive the eta, the wave impedance. Again, for this lossy case. So the same, we use the Maxwell equation. I think we can directly use this equation. Okay, however, the result is your hy will equal to something here. Okay, I think we don't need to derive the details for that, but we will obtain the result like this one. Your eta is j omega mu over gamma, and which is the square root of mu epsilon. This is a lossy wave impedance, and you can find, there is a table, right? Did you see? Do you have the table on your poster? The table. Which number of the table? Can you tell me? For my book is table 1-1.1. For yours also 1.1?
1.2.
1.2. Okay. The same one, right? Okay. Yeah, this is an open book test, so if you know the table, maybe it's easier to find your equation you need. If this is, okay, let's see how much we learned so far, okay? This is a lossless case, which means your eta, epsilon double prime is equal to your sigma equal to your 0. There is no conductivity because it's a lossless. Your gamma is J beta. This is beta. This is beta. Lossless case. Beta equals to your K equals to omega square root of mu epsilon, and gamma equal to J beta. And your attenuation constant, your alpha is 0, which is happy. We are happy that we don't have the attenuation constant. And your impedance is omega mu over K as we derive it. And your skin depth, lossless. So your skin depth 1 over alpha, and your alpha is 0, lossless. Okay, so if this is not a metal, this is some material, of course your wave will penetrate. So your skin depth is infinite. Your conductivity is 0. 1 over 0 is infinite. And your wavelength is 2 pi over beta. Okay, this is important. Beta, the definition is beta. It is always 2 pi over lambda. So your lambda is always 2 pi over beta. See? Okay, beta is how they propagate. The phase constant is always 2 pi over beta. Even for other transmission line, beta is 2 pi over lambda. Okay, for all the transmission line, probably. Okay, we will see. And your phase velocity here, it is omega over k. For here, they are the same. Okay, 3 of them are the same. This is a lossless case. And we derived the lossy case already, right? This is a new thing we derived today. Your gamma equals to j omega square root of mu epsilon, and equals to this ugly part. You have, because you have the sigma, which is lossy. And your beta is the imaginary part of your gamma, and your alpha is the real part of your gamma. And your eta now is j omega mu over your gamma. And your skin depth equals to 1 over your attenuation constant alpha. And for the wavelength and the phase velocity, it is the same. Okay. Okay. We already finished 2. We need to continue one more. I think we can continue one more very fast. Very fast, okay. Let's finish this table today, okay? There is another material. It is not just only lossless, and it is not lossless. It's not just lossless. It is a good conductor, which means your sigma is very large but not infinite. It's not a perfect conductor. It's a good conductor. Good conductor means your sigma is very large. Your sigma is very large. How large? How large? Did you see this ugly? I told you this is ugly, right? We don't like it. So we try to find out something from here. If this term, your sigma is very, very large than this one, which means you don't see this one. Do you understand? If this one is larger than this one, very, very larger than this one, so comparing to one, you cannot see this part. So everything you derive is based on what I say here. Because if you don't have this one, this number, this one here, this equation can transfer to here. One thing we need to deal with is what is I think I ask this question every semester, right? Do anyone know the answer of this one? I will give you 2 bonus points. This is a hard question. Anyone? No? Anyone know what is the square root of minus j? This is a question, math question. What is? How can you simplify this? Do I ask you this question before? Okay, I think because we have many holidays, so I just give you an answer, okay. The result will become something more special than you can imagine. There will be a square root, 1 over square root 2, and 1 plus j, something like that. Okay, but I think it's okay. Don't have time, so you can copy the result. This is the result when you don't have 1, and this one will become this part. Okay, so once you have this part, your real part is this term, and your imaginary part is also this term, because this is 1 plus j, right? So you have the same real part and the imaginary part. And your eta, yeah, I think you just also put the gamma there, you obtain this result, and also if you have alpha, you can obtain your skin depth, and the lambda is the same, Vp is the same. I think that's it. Good conductor, this is your sigma is very larger than your omega epsilon prime. Then you will have this result. Okay, I think this is I already. Good conductor part, I already finished good conductor part. Use this one, and this gamma square. Okay? If you are interested in how to derive it, you need to solve the equation. You need to understand what is the result, and you will obtain the part. You will separate that part. Okay. One more hint to understand this one is you need to, if you really want to solve this one, minus j square root equals to minus j, you take power to 1 over 2. And minus j equals to, you need to transfer to exponential j minus j is 90 degree equals to, this is pi minus pi over 2. So this is j faces 2 pi. And then you this one, so this one equals to minus summation minus j over multiply 2, so it's 4. And then this one is cosine this one plus j sine this one. That's why we have 2 terms.
Okay.
How it's solved. Alright, I finished the class for today. I think we are stuck in the right place, and